Okay, so hello and welcome back. So basically what we will do in this video is, so now let's do a couple of examples on these I have been referring to these transistors as BJPs, which is not exactly correct. You have to call them BJTs, meaning bipolar junction transistor, not transistor or anything like that. So I apologize for that mistake. And now suppose that you have I draw a circuit over here, and we will do a couple of calculations here, not too many of them. So suppose that you have a power supply. This is your positive and this is your negative, and suppose that your power supply goes this way, and then it comes over here through a resistor. It goes to the base of an NPN transistor. So you have an NPN transistor here. This is the emitter of that transistor. This comes down here and it gets connected to your power supply. So that is basically that is an NPN transistor. This is your R of B, and then your collector is connected to the positive supply through a resistor. So this is R of C. And then you have, of course, over here you will have your V of C, and so here your R of C, R of B, and this is your V of S, of course, the power supply voltage. So now suppose that, for example, suppose that this is a silicon transistor. Suppose that this is a silicon transistor. Your R of B is equal to 27 kilo ohm, and your V of S is equal to 3 volts. And you want to find your base current, I of B. So now when you're solving these kinds of circuits, it's important to note what sort of voltage you have here. If the voltage is under 10 volts, as is the case in this particular case, so then of course the voltage drop across your PN junctions become important, because they're a large, basically a large portion of the supply voltage. Or basically, if you take the ratio of those voltage drops to the supply voltage, you get some number basically very close to 1, relative to a case where the supply voltage is very small, meaning that, for example, 0.72, for example, 0.7 to 10 is the same thing as basically divide by 10, you will get something about 0.07, that is 700th. The ratio becomes 700th, right? Whereas and this is, suppose that this is your supply voltage and this is the voltage drop across these PN junctions. That's 700th, very small number. But then if suppose that your voltage drop is 0.7 and your supply voltage is, for example, 3 volts, right? So in that case, basically, that would be something like, I suppose, that would be something like 0.7 divided by 3. That would be the same thing as 0.7 divided by 3. That would be the same thing as 0.2. right? That would be 0.2, which is basically relative to 700th or 7 by 100 is a pretty large number. So in such cases, basically the voltage drop across your p-n junctions have to be taken into consideration. And as a result, basically what you need to do is basically, of course, take those into consideration in your calculation. Meaning that, for example, in this particular case, if I want to calculate the current that goes, my base current, which is the current that goes through this resistor and the base emitter junction and so on and so forth, I need to calculate that using the current that basically goes through the resistor, because I cannot apply the Ohm's law to the transistor. It's a dynamic device, it keeps changing, so it's not possible to catch hold of it. I can catch hold of the resistor because it's like an ohmic linear device. You know what it does, but the transistor is pretty much I mean, it's hard to expect what it's going to do, right? So basically, in such cases, basically you need to decide what the current is based on for example, based on your base resistor. So if I want to basically apply the Ohm's law to this resistor, what I need to do is that well, if I write V is equal to IR, and if this V is the voltage drop across this resistor, and if I know that the resistance of this resistor is 27 kilo ohm, then basically the voltage drop up here is 3 volts. If this voltage is 3 volts, then as you can see, of course, all positive voltages go to ground, meaning that you have this positive voltage goes through this resistor, goes through this p-n junction, base emitter junction, and then ultimately goes to ground. And so what that means is that the base emitter junction and the resistor are connected in series. In a series circuit, basically what happens is that the sum of the voltage drops across the different meaning that, for example, suppose that you have a resistor over here, a resistor over here, and a resistor over here, and they all connected to a power supply. If this is V of S, then basically V1, the voltage drop across this resistor, V2 and V3, then you know that V1 plus V2 plus V3 is equal to V of S, meaning that since these are connected in series, the voltage drop across this one plus this one plus this one must be equal to the supply voltage. And so the same thing happens here. So the voltage drop across the resistor plus the voltage drop across the p-n junction of the transistor becomes the voltage drop of the supply voltage, meaning that V of S is equal to, let's call this voltage V1, and let's call the voltage drop across this V of R of B, and therefore 3 is equal to, or 3 volts is equal to V1, which is the voltage drop over here, which you can take it as 0.7 volts plus V of R of B, and therefore V of R of B is equal to 3 minus 0.7 volts, all in volts, which is equal to 2.3 volts. And therefore V of R of B is equal to 2.3 volts, right? And I'm going to take this supply voltage as having two significant figures, because I'm going to take this as 0.3 volts. because otherwise my calculation will be troubled. So now I know that 2.3 volts is dropped across this resistor, 2.3 volts, and I know that basically the current going through the resistor that I want to calculate. So that's I of B basically, or the current going through this resistor in amps times the resistance of the resistor, which is 27 kilo ohms. So that's basically 27 into 10 raised to the power 3 ohms. And of course you can write kilo ohms over here as well. That's not a problem. Then automatically your units will take care of themselves, but that would make the calculation unnecessarily complicated. So I of B would therefore be basically in amps would be basically 2.3 volts by 27 into 10 raised to the power 3 ohms, and that is the same thing as, now I don't really know, 2.3 divided by 2.3 divided by 27 is the same thing as 0.085. So I can write this as 0.085 into 10 raised to the power negative 3 amps, right? Which is this current over here. So now this is 85,000th of a milliamp. So this was question number 5, and you can call this 85 microamp because you can write this as you can write this as 85 into 10 raised to the power 85 into 10 raised to the power negative 3 into 10 raised to the power negative 3 amps. Now 10 raised to the power negative 3 times 10 raised to the power negative 3 is 10 raised to the power negative 6. So that's 85 into 10 raised to the power negative 6 amps, which is equal to 85 microamps. Micro is the same thing as 10 raised to the power negative 6. So that's basically, for example, how you calculate the base current in this transistor. Now let's do a couple more of these questions. Okay, so now the same circuit, suppose that, for example, I change the supply voltage to a little bit. I keep it as a silicon transistor, and I will change these values a little bit, and let's see what happens to the base current. So suppose that, for example, your base transistor changes to, for example, 220 kilo ohm, and your supply voltage goes up to 10 volts, and now you want to calculate your I of B. So now that basically the supply voltage has been increased to 10 volts, then the voltage drop across the PN junction is not important anymore. Meaning that now I can just simply assume that the whole voltage is being dropped, the whole supply voltage 10 volts is being dropped across the resistor. Which means that then basically applying the Ohm's law to the to R of B, I will have V is equal to I times R, which is the same thing as basically the voltage drop here is 10 volts, and that is equal to I, the current going through here, which is ultimately I of B, in amps times R, and my R, the resistance here is 220 kilo ohms, 220 into 10 raised to the power 3 ohms. And that means that basically I of B in amps, I of B in amps would be, now it's not necessary really to write amps here if the numbers are not. So I of B, and then I of B is the same thing as basically 10 volts to 220 into 10 raised to the power 3 ohm, and that is the same thing as basically 1 to 22. 1 to 22 is the same thing as, I don't know, 1 to 22 is the same thing as 0.045. Taking two significant figures, 0.045 into 10 raised to the power negative 3 amps, and then I can write this as 45 into 10 raised to the power negative 3 into 10 raised to the power negative 3 amps, which is equal to 45 into 10 raised to the power into 10 raised to the power negative 6 amps, which is equal to 45 microamps, right? So this was another part of this question. Another part of this question. Now let's calculate a little bit. Let's do a couple of calculations as well on this voltage here. Okay. So basically what we are discussing here, for example, why you should be able to calculate this voltage, that all basically is important in this book, meaning that of course one thing that you need to keep in mind is that, for example, if you want to learn, let's say you want to learn electronics, preferably you should do it based on one single system and not mix things up, learn something from here, learn something from there, something from YouTube, something from this book, that book. It just doesn't work, you know. I have tried that enough. It just won't work. So you need to find a sound book for anything that you want to learn. You need to find a sound book and follow that book. And then, of course, for example, reactance in this book has been discussed in a certain way. If you go to some other book and consult some other book, reactance, of course, reactance refers to the same phenomenon. But then in some other book, it's been discussed probably in a different way, most probably in a different way. And then if you want to understand basically what that book tells about reactance, of course you need to understand all the other things that have been discussed in that book, right? So now in this book, basically it's important to be able to, for example, to calculate these voltages, and then gradually as we go through this book, all of these things come together, and basically using all of these pieces of knowledge that you put together, you will be able to essentially do certain basic things in electronics, meaning that you'll be able to design basic circuits in electronics, and then basically then you will be able to, for example, take this, once you finish this book, then you'll be able to find good books like, for example, The Art of Electronics, and then start doing experiments on your own, meaning that this book alone will give you a good solid foundation of electronics. The very basic necessary things are all discussed in this book properly, And then after that, of course, if you, whatever it is that you want to do in electronics, then of course you have to do on your own. And for that sort of purpose, you need to get some book, like, for example, The Art of Electronics. The Art of Electronics is some book that assumes that you know the basics of electronics, and then it gives you all of these little circuits, and then you have to experiment with those circuits. And it's just like it would take a lifetime, of course, to finish that. A book like The Art of Electronics, of course, the book is not supposed to be finished by anyone. It rather should be used as some sort of reference or something like that. So if you basically follow this system, and I have, of course, I have done so all the way up to basically 2/3 of the book or so, even a little further than that. It gives you a very good and sound foundation of electronics. So, but then you need to understand everything as you go along. For example, you need to be able to for example, calculate this voltage over here, which is discussed here, right? And one good thing that I have seen in this book is that it doesn't discuss things which are not important. For example, there is all of these books that talk about, that are supposed to teach you electronics, right? But then you buy the book, you pay a lot of money for a book, $20, $30, $40, $50 for a book, and then the book arrives. The book talks about different types of batteries. For example, this is zinc battery, this is oxide battery, this is, I don't know, silver battery, this is the size of this battery, this is the shelf life of that sort of battery. These are the advantages and disadvantages of, but this, well, I mean, what can I do with all of this information about all of these batteries? It's just not relevant. What I wanted to learn was really electronics. I don't care about batteries, right? So most of these books are just, I just don't know why they write all of these things in their books. It just doesn't make much sense, any sense really. So, but this book, I find it to be absolutely amazing. The way that it has been written, just amazing. Okay, so, and I basically, I do highly recommend that you buy a copy of this book. It's just an amazing book. So now if basically we got 45 microamps for the base current. Now let's do a couple of calculations for this V of C, or they have called it V of O here, which is basically, I think it refers to V of output, for example, because this voltage is usually used as output for some other circuit. In some circuits you want to control some other circuit, so this voltage is basically a voltage that changes with, essentially you already understand that basically this voltage keeps changing with changing the current over here. As you change the current over here, the current over here changes, and meaning that as you change the base current, your collector current changes. As a result of that, this voltage drop across this transistor changes. And so this voltage, then you will be able to, you have all kinds of control over this voltage. You can change it as much as you want, and then you can use that as you can use that voltage in order to control other circuits. So, or you can use it, for example, as I don't know, some sort of amplifier or whatever it is that you want to use it for. Now, suppose that you have the same silicon transistor, and basically you want to calculate your V of C, you want to calculate your V of C if R of B is equal to 100 kilo ohm. If R of B is equal to 100 kilo ohm and V of S is equal to 10 volts and R of C is equal to 1 kilo ohm. R of C is equal to 1 kilo ohm and basically beta is equal to 50. And beta is equal to 50. So your base resistor is 100 kilo ohm, your collector resistor is 1 kilo ohm, your beta is equal to 50. It's an NPN transistor silicon, and your supply voltage is 10 volts, and you want to calculate this voltage over here. So, and of course, if I get the chance, I will also show you one of these circuits on a breadboard. Recently, I haven't actually had the opportunity to actually do any practical work, but hopefully sometime we will hook one of these transistors up to a power supply, and then I'll show you basically all of these voltages and everything. And of course, hopefully you already have the basically electronics bench, like a simple oscilloscope, a simple signal generator, a power supply, a couple of meters, amp meters, voltmeters, and things like that. Okay, so now in order to calculate this voltage, first, I mean, you need to calculate this voltage, the voltage that is dropped across this PN junction. What you need to do is that of course you don't really know what is the voltage drop across the PN junction of this transistor, because, well, you cannot calculate that directly. You have to calculate that based on the voltage drop across this resistor. And this resistor, if you want to calculate the voltage drop across that, if I apply Ohm's law to this resistor, V is equal to IR, then basically the resistance of this resistor I already know, R of C is equal to 1 kilo. The current going through that I do not know, so I need to calculate that somehow, and then put that in this relationship to get this voltage, which is the voltage drop across this resistor. So what I'm going to do, but you already know that basically the beta of this transistor, which is the collector gain of this transistor, is basically beta is equal to I of C to I of B. Now, if I am able to, I already know what my beta is. If I can somehow calculate I of B, the current going through the base, then I will be able to calculate I of C. And that I of C would be this current over here. I will substitute that current over here, and then using that I will be able to calculate the voltage drop across this resistor, and then using that voltage drop I will be able to calculate the voltage drop across the PN junction of the transistor, which is this V of C that we ultimately want to calculate. So let's see how we can do that, basically that whole calculation. Okay, so here basically what we want to do is that we know what is the supply voltage, 10 volts. What is basically, we have a resistor here, we know the value of, we have a resistor here, we know the value of, we know the beta of this transistor. This is an NPN transistor, and basically we have some voltage here, and that voltage you can think of as the collector emitter junction voltage of this transistor, because the emitter is grounded, is connected to ground, and so the collector voltage is this point, and this voltage is being, if you measure this voltage with respect to ground, of course, then you're basically measuring the collector emitter junction voltage of this transistor, right? And of course, since by convention all voltages in normal situations are basically measured with respect to ground, you are kind of coming up with some output voltage that when you use this basically this circuit. So that's basically the whole situation. And so now the point of such circuits is that of course you can do all kinds of things with these circuits, meaning that you can control this voltage in any way that you want. And the way that this circuit works is that assuming that you keep this voltage basically constant, meaning that you're not playing with this voltage V of S, if you make changes to this resistor, of course the current in the base current is going to change. The base current changing is automatically going to change the collector current, because the beta of your transistor is going to determine what sort of collector current you're going to have based on your base current. And that is based on this algebraic equation that basically beta times I of B is equal to I of C, meaning that whatever sort of I of B you have, and that you can control, of course, using this resistor, that base current is being multiplied by your beta, and this beta is set for any transistor that you pick for this circuit. That base current is being multiplied by your beta, and that gives you the collector current. And then what that means is that then, because the collector current in this scenario is basically set, then there is some predetermined current flowing through your collector, meaning that there is a predetermined basically current flowing through this resistor as well, because this resistor is basically in line with or in series with your collector current, basically. Now, any current going through any resistor is going to basically result in some voltage drop across that resistor, depending on your power supply, meaning that V is equal to IR. Basically apply the Ohm's law to the resistor. We know the resistance of this resistor. We know the current going through it. So there is some voltage drop across this resistor. And then in turn, in any series circuit, the sum of voltage drops across all of your loads. When you add them together, that adds up to the power supply voltage. That means that basically, if you think about this, basically this part of the circuit over here, which is your collector resistor, and the p-n junction of your transistor, which I show I show this with a, let's call it just a simple diode, for example. And then you have over here, you have the power supply hooked up to the whole thing. So now basically normally what happens is that if I had this type of circuit, and if I didn't have the rest of the transistor and this resistor, only this thing over here, then basically I wouldn't have any control over the current in this loop. The only way that I could control the current is that, for example, I would have this R of C over here, and then by changing this voltage I could change the current going through this resistor, and thereby controlling the whole current going through the circuit. But then over here the interesting thing is that by changing this current in the base, I can actually have control over the current going through the collector current, which is this part over here, and as a result change the voltage drop across this resistor, right? And then of course these two components are in series with one another, meaning that basically you have your V of S here, there is some voltage drop here, some voltage drop here, and these two voltage drops have to be equal to the supply voltage. Which means that basically if I know basically the voltage drop across this resistor, the rest of the voltage has to be dropped across this diode, right? Which is the PN junction of your transistor. Now, what happens here is that I already have control over the current in this circuit without changing the power supply voltage, because I can change this resistor over here, the current over here changes, and as a result, and based on this relationship, the current over here changes. So I can change the current in any way that I want. And by changing the current, the voltage drop across this resistor changes. Changing the voltage drop across this resistor, meaning that the voltage across this diode changes. And that means that the voltage of this point, call it V of C for example, is changing based on the changes that you make in the current in the base of your transistor. That's basically how a transistor works, right? Very clever way of doing things. Otherwise to change the current in this loop, you would have to either change the power supply voltage or change the value of this resistor. But here you don't have to do any of those two things. You can keep the power supply constant. You can keep this resistor constant. The only thing that you need to do in order to change the voltage drop across this resistor is change this current. The transistor is going to regulate the current going through this loop for you, and then as a result the rest of the things are happening in and of themselves. I mean, they are going to just simply going to follow. And that's basically how a transistor basically works, right? Now this kind of understanding, of course, needs a little bit of basically experience with these circuits, meaning that the first time that you read this in a book or something like that, you are not going to get that. But then over time you will be able to do a whole lot of different things using a simple transistor, which is of course amazing. And of course before basically all of these things were possible, we used to do and basically you already know that basically the current going through the power consumption of this circuit is next to nothing, meaning that, for example, the current, the base current of a typical circuit, for example, something like this, is on the order of, for example, microamps or something like that. For example, 5 into 10 raised to the power negative 6 amps or something, which is absolutely nothing. But then we used to do this sort of thing using vacuum tubes, and then these vacuum tubes, as you have probably seen in vacuum tubes, there is something which is actually called a heater in the vacuum tube, and then you have, I don't know, watts of power for first of all, that the tube has to warm up, and it has to get warm enough so that it can start functioning. And it would be like one of those 100-watt bulbs that we used to use for lighting in homes. And they used to use a whole lot of power, meaning that, for example, in any typical electronic device that we had at home, there was this big power supply transformer, and it had to supply 6 volts to the heater, and then there had to be 300-400 volts on the basically the thing had a whole lot of parts, and I'm not at all proficient with these vacuum tubes, but of course we know that basically they used a whole lot of power, meaning that you had to use a whole lot of power in order to do simple things. Now these transistors, what they do is that they do much more complicated things, and you have much more control over the flow of electrons by using some power which is absolutely next to nothing. For example, 5 microamps you're consuming in this circuit, so that you can regulate the flow of electrons almost in any way that you want, depending of course on your transistor and the type of your transistor. So that's the beauty of these transistors, and that's basically how wonderful type of devices they are. So now, in order to basically, for example, calculate the V of C in this circuit, what you need to do is that, so as we discussed here, so first I need to calculate the base current. Once I know the base current, I put it in this equation, and as a result I will be able to calculate the collector current. Once I know the collector current, I know the current going through this resistor over here. And if I know the current going through this resistor, as a result I know how much voltage drop there is across this resistor. The voltage drop, basically I can put it in this equation. I have the voltage drop, I have the resistance. There is the voltage drop. I already know how much voltage drop there is across this resistor, and as a result I will be able to calculate the voltage at this point in the circuit, which we can call the output voltage, V of O or V of C, or whatever you want to call it. And as a result, basically, then you will be able to use that voltage for any sort of application that you need. So that's basically what you need to do here. But then it's important to understand basically the way that the transistor generally works, meaning that you're changing this current, you are making changes to this current. As a result, some changes are induced in the collector current. as a result, the voltage drop across this resistor is changing, and as a result, the voltage of this point is changing, and that's basically how this circuit is working, right? So now, how do I calculate the voltage drop? How do I calculate the base current of this transistor? So I already know how much voltage drop there is across this resistor, because the power supply up here is 10 volts. And this, as you can see, this resistor is basically going over here through the base emitter junction to the ground, right? Now, since my power supply voltage is 10 volts, so I know that basically, and we have agreed before that when the power supply is at least 10 volts, then we are going to simply ignore the 0.7 volt voltage drop. We are going to simply forget the 0.7 voltage drop across the PN junction of the transistor. So that means that basically from here I'm already connected to the positive pole of the power supply, and the voltage up here is 10 volts, and this and over here, from here, if you take the path and go to the ground, you will come across only the resistor, which means that the whole power supply voltage is dropped across this resistor. That means that the voltage drop across this resistor is 10 volts, meaning that there is 10 volts voltage across the terminals of this resistor. And so as a result, I can write V is equal to IR, meaning that I will be applying the Ohm's law to this resistor only, and this voltage is the voltage across the resistor, and that is 10 volts. And the current going through the resistor, that's what we want to calculate, times R, which is the resistance of this resistor, and that is 100 kilo ohms. So that's 100 into 10 raised to the power 3 ohms. And thereby I is equal to basically 10 volts divided by 100 into 10 raised to the power 3 ohms. And there you have basically 10 raised to the power negative 4 volts to ohm, which is the same thing as 10 raised to the power negative 4, basically volts to ohm is the same thing as amps, right? So that's basically your base current, meaning that I can say that I of B is the same thing as 10 raised to the power negative 4 amps. Now, usually I don't write basically these numbers in terms of milliamps or microamps or that sort of thing. Sometimes it's necessary to do that, meaning that, for example, it depends on what you're doing. Usually, when you're working with test equipment is usually based on milliamps, microamps, millivolts, microvolts, and so on and so forth. So you need to be able to, of course, to convert between all of these things in your mind. And then when you're working with test equipment, usually the scientific notation is not very relevant. Meaning that, for example, this current, if an electronics or an electrical engineer were to talk about this, they would call it I of V is equal to 10 raised to the power negative 4 amps, which is the same thing as basically, for example, 10 raised to the power negative 1, 10 raised to the power negative 1 into 10 raised to the power negative 4, 10 raised to the power negative 3, 10 raised to the power negative 3 amps. And that would be basically 0.1 into 10 raised to the power negative 3 amps, which is the same thing as 0.1 milliamps. But nobody talks about 0.1 milliamps. They usually, this kind of current, when your current is less than 1 milliamp, then you have to jump to micro, meaning that you have basically, you normally have kilo, which is 10 raised to the power 3. Then you have milli, which is 10 raised to the power negative 3. Then you have micro, which is 10 raised to the power negative 6. And then you have basically 10 raised to the power negative 9, which is I suppose nano, and then 10 raised to the power negative 12, which is 10 raised to the power negative 12, which is pico, and so on and so forth. So you have to jump back as your numbers get smaller and smaller. Meaning that this number, if I were to express it in microamps, for example, I would write it as 0.1 into basically milli is 10 raised to the power negative 3 amps, right? And then I could write this as, in order to convert, now I'm not very good at converting from milli to micro, because I actually never done that before. While I was working with electronics, I never worked with microamps. That was the kind of thing I never had to do, so I don't know how to convert that in my mind. Which means that basically, but it's simple, meaning that, for example, this is 0.1 into 10 raised to the power negative 3. And then since you want to express that in micro, you can multiply it with basically micro and 10 raised to the power negative 6. Write that in the numerator, that in the denominator, because they are the same values, meaning that you're multiplying this by a factor of 1, meaning that you're not changing anything here. And then the whole thing is in amps. And then of course you can see that so then 10 raised to the power negative 3 and 10 raised to the power negative 6 you can cancel out, or you can simplify. 10 raised to the power negative 3, and so this is the same thing as 0.1 into 10 raised to the power 3 microamps, which is the same thing as 100 microamps, right? 0.1 into 10 raised to the power negative 3 into 10 raised to the power 3 is basically 100. I'm sorry, is it 100? That's 0.1 times 1,000, which is 100 microamps. So an electronics technician or engineer, basically they would call this current, they would call it basically 100 microamps. But as you can see, it's a lot of trouble. It's a lot of trouble to convert from basically that current to microamps. And since we are right now not working with any test equipment, it's not necessary to do that, unless, of course, it does make sense, because ultimately you want to work with the test equipment, and ultimately you do actually need to be able to do that in your mind. Otherwise you cannot always be writing on a piece of paper. It just makes no sense. So so we will actually do that until we are proficient with that part as well. Fair enough. So then basically the base current of this transistor is, and of course then once you do this type of calculation long enough, you will come up with basically some specific ways in your mind that you want that, since, for example, this is milliamp, this is microamp, when you want to convert, you have to multiply it by this factor or that factor to convert. And so after a while it becomes pretty simple for you, or for us. For me, it's not simple either. I can convert between milli and kilo and mega and giga and that sort of thing, but when things get a little bit smaller, then I have trouble down there on the other range of the spectrum. So this is there is a current of 100 microamp going through the base of this transistor, right? Now, the next step would be to calculate the collector current of this transistor, which is what we will continue in the next video. Thank you.